So here the next part of the chapter is, that is 17 group halogens. So in this halogens, why they are called as halogens? They are halogens because the word halo means salt forming nature. They have salt forming tendency. Second is they are 17th group or 7th A group elements. 7th A group elements, that is P block. They belong to P block and their general electronic configuration is ns2 np5. It is because number of valence electrons in halogens, if you take, that is valency electrons, number of valence electrons is equal to 7, and the group valency is equal to, that is group number -8, which is equal to 7 minus 8, which is equal to -1. -1 is the group valency. So if that is the case, then what are the elements which we can consider the halogens? So if you take the elements, for example, if you are taking the elements if you take, that is fluorine, atomic number 9, chlorine, atomic number 17, bromine, atomic number 35, fluorine, bromine, iodine is, again you add that is iodine is 53. For 35 you add 18, you get 53, and astatine, fluorine, bromine, iodine, and astatine is 85. 80 is astatine. Here F is fluorine, then chlorine, then bromine, then iodine, and last one is astatine or astatine. So here if you go for the general electronic configuration, helium of, that is 2s2 2p5, and chlorine is neon of 3s2 3p5, bromine is argon of 3d10 4s2 4p5, then helium, neon, argon, krypton 4d10 5s2 5p5, then helium, neon, argon, krypton, xenon 4f14 5d10 6s2 6p5. So you are finding that here, the last 7 electrons are entering into, that is ns orbital and np orbital. So therefore the general electronic configuration of the 7th A group family is definitely ns2 np5. So if you go for the general properties discussion, that is general properties, if you go for the general properties of halogen, general properties of halogens, you take fluorine, bromine, iodine, and astatine. Actually fluorine and chlorine, these are non-metal gases, non-metal and metallic gases. Bromine is a liquid non-metal, and iodine is sublime solid non-metal, and astatine is a radioactive metal. And if you go for the colors of the astatine, here if you go for colors, different colors, fluorine is pale yellow, and chlorine is greenish yellow, greenish yellow color, bromine red color, reddish brown, iodine is violet color. So different halogens have different color formation tendency because they try to absorb the different spectrum. For example, there is one reason why the fluorine is showing, what is the reason the fluorine to show pale yellow color, and what is the reason for iodine to show violet color. In the electromagnetic spectrum, if you take fluorine being small size, if you go for the fluorine, it has so many unique properties. Fluorine, if you take, that is smaller atomic size, fluorine has smaller atomic size, then it has low bond enthalpy, high oxidizing power, then this fluorine, it is highly electronegative, then it has highest standard oxidation potential, which is equal to plus 2.86 volts. It has absence of d orbital. So all these points you have to keep it in mind. And interestingly, what is happening here is fluorine, because of its smaller atomic size, fluorine gas always try to absorb the smaller size. That's why it will try to absorb the radiation. If you go for the electromagnetic spectrum, violet, indigo, blue, green, yellow, orange, red. Red has maximum wavelength and minimum energy. And if you go for violet, if you take, it has minimum energy, minimum wavelength and maximum energy maximum. So because of its large size, iodine, because of its large size, it will try to absorb. Fluorine, because of its small size, it will try to absorb the radiation of it absorbs the red color radiation. Absorption is red, but when it gives yellow color. Yellow is the complementary color. Similarly, iodine is very large, so it will try to absorb the red color. Iodine is trying to absorb, so it will try to absorb the violet color. It will try to absorb the same situation is taking place here, different complementary colors. So the same explanation you can give for iodine, which is violet color. So this violet and yellow, these are complementary. These colors are called complementary colors. So because of the vacant orbital present in their atomic orbitals also, they can easily, that is, accept the radiation and make the electron to get excited, and they can acquire the new color formation. And this is the reason why we say that the halogens have different color formation. So if you go for the halogens, because sources, let me continue with the topic, that is, they are called as halogens because they have the mineral or salt forming tendency. Mineral salts or salt of minerals forming tendency. That's why they are called as halogens. So if you take the different mineral ores of fluorine, chlorine, bromine and iodine, so they have different sources. For example, if you take calcium, if you take fluorine, it is available in the form of fluorspar, then 3Ca3PO4 taken twice of CaF2. This is called fluorapatite. Then chlorapatite, 3Ca3PO4 taken twice of CaCl2. Then you can take it as chlorapatite. That means here you are finding that chlorine is present over here. Here fluorine is present. Then you can take KCl. That means, for example, if you take fluorine, Na3AlF6. Na3AlF6 is nothing but cryolite, which is an important mineral ore. Then you can take carnallite, KCl, MgCl2, 6H2O, is available in the form of carnallite, then you can take NaCl, which is brine solution, it's called as brine or rock salt, then NaIO3, then NaBrO3. We can call them as seaweeds, so on and so forth. So these are all some of the important sources of the mineral ores of the halogens, depending on their availability. And if you go for the periodic trends, in halogens, so for example, if I am taking the first case, that is electronegativity, if you take decreasing order of electronegativity, yes, halogens, if you take fluorine has the highest electronegativity, so fluorine is more electronegative than chlorine, is more electronegative than bromine, is more electronegative than iodine. In fact, we consider the fluorine as the superhalogen. We consider it as superhalogen. It has high enthalpy of hydration, and on Pauling scale, its electronegativity value is equal to 4.0. Bond energy, if you go for bond energy in halogens, if you take in halogens, that is chlorine is greater than, bromine is greater than, fluorine is greater than iodine. So here chlorine is greater than bromine is greater than fluorine is greater than iodine. Here you are finding that fluorine has less bond energy than that of chlorine and bromine. It is because of the reason that is it has that is non-bonding, because F2 being small in size. The reason is small in size, and if you go to the actual structure of fluorine, it has non-bonding pair of electrons. So it has all the 3 lone pairs. Each fluorine is having 3 lone pairs. So you find that there is abnormal electron repulsions taking place. Electron repulsions of lone pair of electrons takes place. So as a result, instead of gaining more energy, the fluorine will try to show very less energy, and it is also having, that is absence of d orbital. One more reason is it has absence of d orbital, and its enthalpy of hydrogen is very high. So that is the reason why you find that abnormally the fluorine gas has lowest bond energy than that of the chlorine and bromine. Then if you go for the last one, that is electron affinity, if you take in the halogens, if you are taking in the halogens, then yes, chlorine is greater than fluorine is greater than bromine is greater than iodine. So you find that electron affinity of chlorine is greater than the electron affinity of fluorine because of the less electron repulsions. Though the chlorine is having more or larger atomic size, you find that in the chlorine less electron repulsions takes place than the fluorine. But fluorine, because of its small size, more electron repulsions takes place. So therefore it cannot release more amount of energy when it is trying to gain one electron. Actually, the electron affinity property of all the halogens can be studied through the Born-Haber cycle. In the Born-Haber cycle, we will first convert the molecular halogen to atomic halogen, and that atomic halogen, it will try to gain an electron and it forms the uninegative ion. Once it forms a uninegative ion, it is involved in the electron affinity, and once it is involved in the electron affinity, some amount of energy is released during the formation of uninegative ion. That uninegative ion can be shown here. That is, if you go for electron affinity, that is, if you take half mole of chlorine gas, by supplying a bond dissociation energy, it becomes atomic chlorine gas. This atomic chlorine gas, now it gains one electron and it forms uninegative gaseous ion. So this is electron affinity. Then enthalpy, this uninegative gaseous ion, when it is dissolved in water, it becomes Cl minus of aqueous. So therefore enthalpy of hydration involves. So that means various energy changes are taking place such that you are converting the molecular form of the chlorine gas to the aqueous form of uninegative chloride ion is converted. So series of steps takes place, and this proves that the electron affinity for chlorine is much more greater than that of the fluorine. So fluorine, because of its small size and more electron repulsions between the non-bonding pair of electrons and the bond pair of electrons, surprisingly you find that the fluorine will have lesser electron affinity than that of the chlorine. So therefore you can find this kind of order in the case of halogens. And if you go for the other cases, like apart from that, I think I can add one more, that is, if you take the oxidizing power among halogens, if you take also, yes, fluorine is considered as a super halogen. So next comes chlorine, next comes bromine, and next comes iodine. So therefore it is proved that even in the reactivity series, in the electrochemistry, in the reactivity series also, you find that all the non-metals are placed at the bottom of the reactivity series, which has the positive standard that is reduction potential, and all the metals which are more reactive, metals which have more reactivity are more reducing in their nature. So all the highly reactive metals are placed at the topmost position of the reactivity series, and all the non-metals which are having the highest SRP value, which are more oxidizing in nature or which have more oxidizing power, are placed at the bottommost region of the reactivity series. And you know very well that fluorine is the only element in the entire periodic table which has the highest electronegativity. More is electronegativity, more is the oxidizing power. So when you go for more oxidizing power, you can say that fluorine is placed at the bottommost region of the reactivity series, and it proves that definitely here, because of the various exceptional reasons, anomalous reasons, fluorine is definitely more oxidizing than the remaining halogens or their counterparts of halogens. So here the next part of the discussion is, that is, if you go to the chemical properties of halogens, if you take, let us discuss something about the oxidation states. If you take the oxidation states, that is, we all know that the general electronic configuration of the halogens is ns2 np5. So like if I am going to take, that is, I'll consider the ns2 np5 as, suppose if I am taking ns2 np5, if you take ns sublevel or orbital, it contains 2 electrons, and if you take np5, if I am going to take, that is 1, 2, 3, 4 and 5, this is np5. Of course it has 5 electrons and it has 2 electrons, and this np5 you can just write it in the form of, that is px, this is py, and this is pz. But here what you are noticing here is it contains 1 unpaired electron. So when it is having 1 unpaired electron, if I consider this as, this configuration as ground state, because it contains 1 electron, then I can say that the oxidation state of the halogens, of all halogens in the ground state, we can consider it as, that is either +1 oxidation state or -1 oxidation state. If I take the +1 oxidation state, for example, if I take +1 oxidation state, you can take for example, you can take Cl2O. The best example for +1 oxidation state is, you can take chlorine monoxide. -2 is the oxidation state of oxygen, valency of oxygen is -2, so chlorine is +1. For -1 oxidation state, you can take you can take halo acids. If you take halo acid, you find that the fluorine definitely shows negative oxidation state. And even if you take the interhalogen compounds, like not only this, you can also take ICl. If you take ICl, yes, chlorine is -1, so the iodine is carrying +1 oxidation state. So this 2 cases you can take it in terms of, that is +1 and -1 oxidation state, that is +1 and -1 oxidation state. So I can say that these two comes under, that is, both are having +1 oxidation state. Iodochlorine and dichlorine monoxide is having +1 oxidation state, and in hydrogen fluoride, fluorine is having -1 oxidation state. And now I want to transfer or promote one of the electron from np orbital to nd orbital, and this is the ground state configuration. Go for the next case, that is now promoting one electron. So I am going to take again ns2 electrons. If I take, so there are 2 electrons here, then here, that is 1, 2, then this is 1, 2, 3, 4, 5. So this I can take it as np5, this is ns2, and this is nd Okay, this I am taking it as ND0, but right now I am going to convert this to first excited state. If it is first excited state, then already we have 1, 2, 3, 4, 5 electrons are there. So one of the electron from the NP5 orbital, you try to promote it to ND orbital. So if that is the case, then that means the new configuration, that is we have to promote it. So still it is in the ground state only, the same ground state I have taken. So I'll just take this as the ground state configuration, take this as ground state. Now convert this to excited state. In the excited state, I can take again NS2, that is 2 electrons, again go for, and now this is going to become NP4 with 1, 2, 3, 4. This is Px, this is Py, and this is Pz orbital, and one electron is promoted. So here 1, 2, 3, 4, 5. So this is 1 electron, so this is going to become ND1. So and this is going to become first excited state configuration. But interestingly, what you're noticing here is we have 3 unpaired electrons. Here we have 1 unpaired electron, here we have unpaired electron, and here also we have unpaired electron. So what are the oxidation states which are possible here? We can take +3 oxidation state. You can take +3 oxidation state. The oxidation state is +3. So if it is +3 oxidation state, then what are the examples you can take here? Examples you can take, the best example is ClF3. The best example is ClF3, that is interhalogen compound, trifluorochloride. The oxidation state of chlorine is +3, and you can also take the oxyacids of chlorine. You can take, that is oxyacids of chlorine. You can take HClO2 also, chlorous acid, which is +3 oxidation state. So these are the 2 examples where we can give for +3 oxidation state. And next from here we will go for the next oxidation state, that is you promote one more electron from px orbital to the ND. This is dxy. Let us take this as dxy. This is dyz. So if it is dyz, then this is going to become, the next configuration is going to become, that is NS2 of 2 electrons. Take the promotion of electrons 1, 2, 3. So this is going to become NP3 now. If it is NP3, so therefore now this is Px, Py, and this is Pz. So therefore you borrow one more electron to the ND2. Now this has become ND2, 1, 2, 3, 4, 5. So take 2 electrons here. So right now you have, this is dxy and this is dyz. This is dyz, and now this has become the second excited state configuration. If it is second excited state configuration, you are finding that the total number of unpaired electrons in the given orbitals are 3 plus 2, total 5. So here the oxidation state can be +5. If it is +5, again you can take one the +5 oxidation state. Yes, so here you can take some examples. Here for +5 oxidation state, you can take BrCl5, where in which the bromo group is +5 oxidation state, and you can also take, that is chloric acid, which is again +5 oxidation state. So we have one more configuration, that is the third excited state. If you go for the third excited state, let me explain here the third excited state. That is, I can take here, yes, you can promote one electron from the NS2 configuration to ND2. So this is going to become, that is first orbital is NS1, one unpaired electron, then NP 1, 2, 1, 2, 3, then this is ND3. So 1, 2, 3, 4, 5. So 1, 2, 3. This is ND3, and here it is NP3. So therefore this is Px, this is Py, this is Pz, and this is dxy, and this is dyz. So what is happening here is like we have 7 unpaired electrons, 1, 2, 3, 4, 5, 6, and 7. So therefore this is the third excited state, and it has oxidation state equal to +7. So the examples of the +7 oxidation state, you can take number of examples. You can take, that is the best example is, that is IF7 interhalogen compound, in which iodine is +7. Perchloric acid, the oxidation state is again +7. Perchloric acid, HClO4, and you can also take chlorine heptoxide, where in which the chlorine is having +7 oxidation state. So it's starting from -1. That means in a nutshell, how do you conclude this? in the conclusion you can take, that is starting from -1 to, that is +1 to +3 to +5 to +7 oxidation states are possible in the case of halogens. So the least oxidation state, for halogens is -1, and the maximum oxidation state for the halogens is +7. So therefore various cases of -1 to +7 already we have studied. -1 oxidation state is possible in the case of ground state, and +1 oxidation state is possible in the case of the third excited state, and these are the corresponding examples what we have taken in the case of least oxidation state to the highest oxidation state. So if you go to the next part of the chemical property of halogens, that is you can go for, that is solubility of halogens. If you take solubility of halogens follows the order, decreasing order, that is decreasing order of solubility among halogens. If you take, that is fluorine is more soluble than chlorine, is more soluble than bromine, is more soluble than iodine. Iodine, because of its large size, the iodine is almost insoluble in water. But if you take fluorine, in the case of fluorine, that is fluorine gas when reacts with water, under cold conditions, you can take HF gas plus O2 gas. This is one reaction where you need to remember. So balance the equation. So that is we have 2 oxygens, so take 2 over here and take 4 over here and take 2 over here. And if the same fluorine gas, if it is reacting with water under hot conditions, in the case of steam, so you find that here, that is HF gas plus O3 gas. So here balance the equation, take 3 over here, then take 6 over here and take 3 moles over here. That means you are finding that fluorine, when it is coming in contact with water, fluorine when it is subjected to hydrolysis, or when it is trying to get soluble in water, it is giving the mixture. This mixture is called, that is ozonized oxygen. But if you go for that is the rest of the halogens, that is chlorine and bromine in particular, chlorine comma bromine, if you treat this as X2, then if this X2 gases, X2 when reacts with water, they give 2 types of acids, one is HX and HXO. HX is called as halo acid, these are called halo acids, and HXO, that is hypohalites. These are called as hypohalites. Then for example, if you take chlorine in particular, chlorine gas when it reacts with water, it forms HCl plus HClO. And similarly, if you take bromine, Br2 plus H2O gives rise to HBr plus HBRO, hypobromous acid. And this is hypochlorous acid, and this is hypobromous acid. So here if you go for the next part of the discussion, apart from the solubility, if you take in the solubility, if you take particularly I2, note one important point what we have to note down here is, that is I2 is a sublime solid, and I2 as a solid, if you put it in water, liquid, it is insoluble. Because the solubility is expressed in terms of free energy, which is positive, and it is non-spontaneous. Iodine, because of its large size, it is insoluble in water, so that's because the change in free energy of the solubility of the iodine is positive, which is non-spontaneous. But however, you can increase the solubility of iodine by treating it with the potassium iodide aqueous. When treated with iodine solid, it forms Ki3 aqueous. Here the solubility increases. This Ki3 forms k plus of I3 minus KI3 minus, this is a soluble complex. This is a soluble complex, and this I3 minus has, if you take I3 minus ion species, this is triiodide species, wherein which if you take the structure of triiodide, if you take, then this is going to become, that is something like you have 3 iodines in the same plane with a negative charge, and we have 3 lone pair of electrons for the iodine, and it undergoes sp3 hybridization, the sp3d hybridization. Here the iodine undergoes the sp3d hybridization, and the 3 lone pairs are occupying the equatorial plane, and the shape of the molecule is going to become linear shape, where the 3 lone pairs are trying to occupy the equatorial plane. So this is the structure of I minus ion, and that comes, in that way we can increase the solubility of, that is Ki3 minus ion of the Ki3 salt. So if you go for the displacement reaction, the next part of the chemical properties, displacement reactions in halogens. Suppose if I am taking one reaction like this, that is Kx plus F2 gives rise to, that is Kf plus X2, where fluorine is acting as an oxidizing agent. So here is X2 is 0. So it is very clear that now X2 is a halogen, and here the halogens are chlorine, bromine and iodine. Then again what we are noticing here is, you take K of X plus Cl2 gas, again it's an oxidizing agent, so you find that this is KCl plus X2 gas. So here you find that here, that is X2 is equal to, that is chlorine means, that is bromine comma iodine only. Of course you need to balance the equation, take 2 over here, that is 2 fluorine, so take 2 over here, take 2 over here. And the last one, if you take, that is again, if you take Kx is nothing but potassium halide here. Kx is called as potassium halide, and take this potassium halide, and now if you are treating it with bromine aqueous, then you find that here, that is KBr plus X2 gas, where X2 is equal to iodine only, bromine KBr aqueous. That means from these 3 reactions, what you are able to understand is, that is, you can just take it as the decreasing order of oxidizing power. OP stands for oxidizing power among halogens. Among the halogens, if you take, yes, you can take fluorine is greater than chlorine is greater than bromine is greater than iodine. So that means what is happening here is, fluorine, if I am going to take fluorine, chlorine, bromine and iodine, if I am going to take, and you find that fluorine can oxidize chlorine, it can oxidize bromine, and it can also oxidize iodine. But at the same time, if you take chlorine cannot oxidize the fluorine, but however chlorine can oxidize the bromine, and it can also oxidize the iodine. Similarly, if you are going to take fluorine, chlorine, bromine and iodine, if you take, yes, bromine can oxidize iodine, but bromine cannot oxidize chlorine, bromine also cannot oxidize fluorine. So therefore bromine can oxidize only iodine, because iodine is at the bottom of the bromine. So bromine can oxidize iodine, but bromine cannot oxidize chlorine and fluorine. Similarly, if you take chlorine, chlorine can oxidize bromine and iodine, but chlorine cannot oxidize fluorine. But if you take fluorine, fluorine can oxidize all three: chlorine, bromine and iodine. So this method of oxidizing, that means this method of oxidizing, the method of oxidizing more, oxidizing less, method of oxidizing less oxidizing halogen by more oxidizing halogen is called as displacement reaction. So here the next part of the discussion here is that is reaction with the H2 gas, reaction of halogens with the H2 gas. If we take, that is, you can take the reaction, that is H2 gas, when it reacts with X2 gas, it gives HX. HX is nothing but a halo acid. It's a halo acid. HX is halo acid. So if you go for HX, so you find that here HF, HCl, HBr, HI. So what are the periodic trends? If you go to the periodic trends of halo acids, if you take in this, the first one you can take, that is melting point and boiling point. Melting point comma boiling point of halo acids, usually it is directly proportional to the increase in the atomic size of halogen, and also that is increase in van der Waals forces, and also that is hydrogen bonding. These are the three characters which you have to keep it in mind. So if you go for the the melting point and boiling point, if you take the decreasing order, HF is much more greater than HI, is much more greater than HBr, is much more greater than, that is HCl. Why this variation is coming in the case of the melting point and boiling point for the halo acids? Actually, if you take hydrogen fluoride is an associated liquid. It has hydrogen bonding. And it also shows the dimeric nature. Only HF has the tendency to form the dimeric nature, and that is why we can say that hydrogen fluoride has the highest boiling point and melting point. And if you go for HI, it is having, after HF it is HI, because the molecular weight or the atomic weight of iodine also, it is very high. And the rest of the halogens, you're finding that there is decrease in the van der Waals forces. So this is one trend which we have to keep it in mind. The next comes, after this you can go for, that is the B bit. If you take this next part of the discussion, if you make the increasing order of acidic strength, so here acidic strength is directly proportional to lesser bond energy between hydrogen and halogen. And the ability for the given halo acid to release the proton is also one important point which you have to keep it in mind. So the increasing order of acidic strength means HF is less acidic than HCl, is less acidic than HBr, is less acidic than HI. So I can say that HI is strong acid, and HF is a weak acid. HF is weak acid since it has strong bond energy. It has strong bond energy between hydrogen and fluorine. There is a strong bond energy. So therefore it, with great difficulty, it is going to release the proton. But in the case of HI, you find that because of the large size of iodine, you find that it has weak bond energy. It has weak bond energy. So therefore we can say that hydrogen iodide is the Hi is the strong acid and HF is the weak acid. So therefore you know very well that always weak acids give a strong conjugate base by release of proton according to the Bronsted-Lowry theory, and strong acids always give weak conjugate bases by release of proton. So therefore since HF is weak acid, HF is a weak acid, so its conjugate base is going to become F minus plus H plus ion, and if you go for Hi, which is a strong acid, gives I minus plus H plus ion. So therefore what the best thing what we can do is, because the hydrogen fluoride is a weak acid, so you can take F minus is a strong conjugate base, so I can add one more, the increasing order or the decreasing order of the strength of conjugate base. If you take Cb stands for conjugate base, so F minus is a stronger conjugate base than Cl minus is stronger conjugate base than I minus. Apart from this, you can take the thermal stability and the bond energy and the bond enthalpy. If you take also thermal stability, it again depends upon the hydrogen and the size of the halogen. So therefore thermal stability of HF is much more greater than thermal stability of HCl, is much more greater than HBr, is much more greater than Hi. So all this we can keep it in mind in terms of the hydrates of halogens. So the next part of the discussion here is, that is action of alkalis on halogens. Actually every halogen has different mode of reaction with the alkalis. For example, if you take fluorine in particular, that is so when you are going for action of alkalis means, I mean to say here alkali is NaOH, or you can take KOH, sodium hydroxide or potassium hydroxide, any one you can take, and you can treat it with halogen under different conditions. You can take cold case and you can also take hot case, and let us see what is happening, what kind of products we are going to get when these halogens, when they are going to react with the alkalis like sodium hydroxide or potassium hydroxide. So here if you are taking the, particularly if you are going to take fluorine gas, so I am going to take fluorine gas, and if I am going to take NaOH is cold and dilute. So if I take fluorine gas in the cold and dilute state, so then interestingly you are going to get sodium fluoride plus oxygen difluoride plus that is H2O. Okay, so to balance the equation here, I think if I am going to take, that is 2 over here, that is total number of fluorine atoms, 2 fluorines and 2 fluorines, 4 fluorines are coming over here, and the number of sodiums are 2. Okay, fine, so I am going to take 2 over here. Then I think if I am going to take hydrogens and 2 oxygens are balanced, and the number of fluorines also, yes, they are automatically balanced, and this is called oxygen difluoride, in which the oxidation state is, that is plus 1 is the oxygen state, and here it is that is 0. So indirectly I can say that the sodium hydroxide is acting as an oxidizing agent, and this is cold case. Now if you go for the same fluorine gas in the case of sodium hydroxide, that is in the case of hot case, then you find that yes, sodium fluoride you are going to get plus O2 gas plus H2O. Yes, directly we are getting oxygen gas over here. That is the difference we should try to make out, and we have 2 hydrogens and 2 okay, to balance the equation, say suppose if I am taking 2 over here, then I am going to take 4 over here, then because you have already 4 hydrogens and 4 oxygens are there, that's why taking 2 moles of water you get 4 hydrogens and 4 oxygens, so take 4 over here. So therefore take 4 over here again, then you take 2 over here. Yes, the reaction is balanced. Then if you go for the rest of the cases, like if you go for chlorine, that is bromine, and iodine, they have altogether different methods of reacting with the NaOH, that is NaOH cold and dilute, and the same NaOH that is hot and concentrated. So taking this into consideration, first I will take only chlorine. With the chlorine I am going to write the reaction. Suppose if I am taking chlorine gas plus NaOH cold and dilute, then you are going to get, this is a disproportionation reaction. It's a kind of disproportionation reaction where the chlorine is going to disproportionate from zero oxidation state to the next higher oxidation state. So therefore here you can take sodium chloride plus sodium hypochlorite plus H2O. You can take, yes, to balance the equation, take 2 over here. Here the chlorine is -1 oxidation state, and here the chlorine is +1 oxidation state. So here this is sodium hypochlorite, you can take, and the same chlorine gas, if you are going to take the sodium hydroxide, that is hot and concentrated, the reaction slightly differs here. That is, you can take sodium chloride plus sodium chlorate NaClO3 plus H2O. This is sodium chlorate, so this is going to become, this is +5 oxidation state, this is -1, and this is 0. So definitely it is a disproportionation reaction. Here also it is disproportionation reaction. Balance the equation, take 5 over here, take 6 over here, and take 3 over here. Then I think the entire reaction has already been balanced. So this is a perfect example. All I can say is this is a perfect example of, that is, disproportionation reaction. It's a perfect example of disproportionation reaction, and more or less the reaction is same in the case of the bromine and iodine also. So that's why what I can do here is, yes, if you take bromine if you take with the NaOH cold, if you take, yes, you get NaBr plus NaBrO, and with iodine also more or less you get the same kind of reaction, that is cold. If you take NaI plus NaIO, and if you take bromine, again in the presence of bromine aqueous, if you take in the presence of NaOH hot, I am not balancing the equation, sodium bromide plus sodium bromate, and here also if you take iodine, yes, NaOH, if you take, that is hot, you get NaOI plus, that is sodium iodate, NaIO3. You can take NaIO3, so sodium iodate. Actually these NaBrO3 and NaIO3, these are called as seaweeds, which are obtained near seashore of the halogens. That's why halogens are salt producing minerals, we call them. That's why the group name is halogens. So the next part of the discussion here is, that is reactivity with the O2 of halogens of X2. So here I can take here something like this, F2 Br F2 okay, that is I'm going to take, that is Cl2 F2 Cl2, then Br2 and I2. So there are actually all the halogens, they form wide number of different oxides are there, but some important oxides let us going to discuss which are useful for us. So suppose if you are going to take for fluorine, I think we can take two types of oxides here. One is OF2 and the other one is O2 F2. And in the case of chlorine, if you take, yes, it forms maximum number of oxides, chlorine, that is it forms Cl2 of O, it forms ClO2, it forms Cl2O6, and it also forms Cl2O7. If you go for bromine also, yes, it is going to form Br2O, BrO2 and BrO3. It forms dimeric form of BrO3. Yes, it forms I2O4 and I2O5. So in fact I can say that particularly if you take the oxides of chlorine, they are powerful oxidizing agents. If you take, for example, if you take OF2, that is this OF2 oxygen difluoride, here the oxygen state of oxygen is +2, and here the oxygen state of oxygen is +1. Here the oxygen state of chlorine is +1. This is +4. This is +3, and this is +7. Here also iodine is +5, and here the iodine is +4. That means you are finding that the oxidation state of halogens keeps changing from +1 to +7. For example, if you take all are good oxidizing agents, if you take fluorine, if you for example if you take OF2, if you are taking, for example, if you take OF2 preparation, sodium hydroxide plus fluorine in the cold condition, yes, it is going to give sodium fluoride plus OF2 plus, that is H2O. So to balance the equation, take 2 over here, take 2 over here, and take 2 over here. Oxygen difluoride has been formed. So now next, if you go for OF2, yes, it can form two fluorine atoms, and total 6 valence electrons are there. So it is, the bond angle is around 103 degrees. Here interestingly you find that the lone pair of electrons repulsions, the lone pair, you find that here the lone pair, the adjacent atoms, if you take the lone pair repulsions of adjacent atoms are greater than the bond pair atoms. That's why here the oxygen in OF2 oxygen undergoes sp3 hybridization, but the bond angle changes from 108 degrees to 103 degrees because of greater repulsions between lone pair electrons of fluorine to that of bond pair electrons of oxygen. So bond angle is decreasing from the 109 degrees 28 minutes to, that is 103 degrees. And likewise, O2F2 also you can prepare directly silent electric discharge. It has open book structure. Then if you take Cl2, all these, the oxides of, particularly the oxides of chlorine, they are powerful oxidizing agents. The disproportionate, and they form oxyacids when hydrolyzed. Then if you go for I2O5 structure, it has one IO5 link, wherein which it has 4 coordinate covalent bonds like this, I2O5. So if you look into the oxides of the halogens, you find that just like the oxides of chlorine, here the oxides of bromine also, they are good oxidizing agents. And the oxides of iodine, they are insoluble solids, and they are used in the estimation of carbon monoxide. And you find that the oxides of chlorine, for example, if you take particularly if you are going to take the oxide ClO2, every oxide is going to give its own oxyacid. For example, if you take ClO2, I think it can give 2 types of oxides upon hydrolysis. That is, it can give HCl, HClO plus HClO2 it can give. If I take then I think you can take HClO2 of HClO3, we can take here, that is, here chlorine is +4, and here the chlorine is +3, and here the chlorine is +5. That means it is trying to disproportionate, and it is trying to give 2 different types of oxyacids. One is chlorous acid and the other one is chloric acid, which different oxidation states which are available for the chlorine dioxide. That we have to keep it in mind. And this is something about the that is reaction of halogens with the oxygens. And apart from this, what we can do is we can go for the next part of the discussion, that is interhalogen compounds. And before going to the interhalogen compounds, reaction of metals, there is one particular topic where the reactivity, reaction with the metals. If you take reaction with metals. If you take these halogens they try to show different types of behavior for the different types of metals. For S block elements they have one kind of behavior, and for the D block elements they have one kind of behavior. For example, if you take sodium, when it reacts with chlorine, yes, it gives sodium chloride, both are monovalent. If you take magnesium, yes, it can also give the reaction magnesium chloride. Magnesium is bivalent. But if you go particularly for the metals like D block elements, for example, copper, when it reacts with chlorine, it always chooses the salt formation of the higher oxidation state salt, that is Cu2 plus. Cu2 plus cupric chloride is formed, but CuCl with this, which is +1 oxidation state, it is not formed. We give priority only for CuCl2. Similarly, if you go for iron and if it is treated with chlorine, you get FeCl3. Give priority for the higher oxidation state chloride, but not FeCl2. But one question I can give you, that is, what if the iron is going to react with HCl, but when iron reacts with this is metal and this is acid. Metal, when it reacts with acid, it always prefers to give the FeCl2, which is having +2 oxidation state, is given the priority, but FeCl3, which is given +3 oxidation state, is not given priority. Of course, the hydrogen gas is evolved. So in the reactivity series, once the hydrogen gas is evolved, when the acid is reacting with the metal, once the hydrogen gas is evolved, the hydrogen gas which is evolved will prevent the metal salt to form to a higher oxidation state, because always the metals will have low SRP value in the reactivity series. So the evolution of hydrogen depends upon the metal salt formation with the lower oxidation state, and that is one reason where we can say only ferrous chloride is going to be formed but not ferric chloride when the metal is coming in contact with the acid, that too particularly the D block element. So the next part of the discussion is, that is, formation of interhalogen compounds. So I can take here, that is something like this xy. Suppose if I am taking x of y of n, if I am taking or x of a, I'll take x of a, I'll take x of a base n, where n can be 1, 3, 5 and 7 only. So here you can take x is the halogen with the lesser electronegativity, and y, that is a, not y, sorry, this is a is the halogen with the greater electronegativity. So for example, because we are saying that means here x is acting as a central atom halogen, and here a is acting as adjacent atom halogen. A is acting as an adjacent atom halogen. Okay, fine. So now how can we just try to justify ourselves? So all the interhalogens with general formula with the x of a of n is given by, that is, you can take ICl, BrCl, then you can take chloro, fluorine, etc. All these are the different interhalogen compounds, and you are finding that iodine, if you compare iodine and chlorine, iodine is having lesser electronegativity than chlorine, bromine has lesser electronegativity than chlorine, and chlorine has lesser electronegativity than fluorine. So if that is the case, that is the first case. Go for the second case, that is interhalogens with the XA3. If you take XA3, the best example what I can give you is ClF3. You can take then BrCl3, CL3 or ICL3 you can take. You can even take ICL3. These are the compounds. And similarly, if you go for the interhalogens with the XA5, yes, we can take BrF5, BrF5, BrCl5 and so on. The last one if you take interhalogens with the XA7, the best example is IF7, iodine heptafluoride. So now the question is how to identify the AX3 type of molecules. I can say that here take ClF3, take BrF5 and take IF7. So ClF3, if you take chlorine trifluoride, if you take the structure of chlorine trifluoride, you can take it here as that is it's in the it's a T-shaped molecule, so take 3 fluorines in this pattern, and the 2 lone pairs are occupying the equatorial position. The 2 lone pairs are in the equatorial position. It's a T-shaped molecule. It's a T-shaped molecule. It's a T-shaped molecule with 2 lone pairs in the equatorial position, and the rest of the 2 fluorines are in the axial position, and one of the third fluorine is again in the equatorial position. It's a T-shaped molecule. ClF3 is a T-shaped molecule. ClF3. Now go for BrF5. If you're going for BrF5, for example, how do you check out this? Actually, I don't know what is the shape or what is the what kind of hybridization is there in it, or what is the shape or geometry, we don't know. That's why, because it's a neutral molecule, it's an interhalogen compound, so I'll use the formula H is equal to half of V plus M. V plus M I'm going to use, where H is the hybridization, V is the number of, V stands for number of valence electrons of the central atom, and M stands for the number of monovalent adjacent atoms which are present in the interhalogen compound. So therefore here if I want to calculate, H is equal to half of, in the place of V, number of valence electrons of bromine 7 plus fluorine is 5. Okay, so H is equal to, that is 12, H12 by 2, which is equal to 6. 6 is nothing but sp3 d2 hybridization. If it is sp3 d2 hybridization, it should be octahedral, but one atom is missing. So what I'm going to do is I'm going to put it in the octahedral plane like this. So take the bromine, take the 4 fluorines like this, fluorine here, fluorine here, fluorine here, and fluorine over here. So take the octahedral plane first, assign the octahedral plane. So the best thing what I can do here is I'm going to take one fluorine over here like this, and one of the lone pair I'm going to put it in the octahedral plane like this. Octahedral plane we can put it. So this is something like square pyramidal, I can say. The shape is square pyramidal shape for BrF5 molecule, and even for IF6 also, IF7 also we can do the same thing. That is in IF7 the fluorine has H is equal to half of V plus M. So that means half of number of valence electrons of iodine 7, and the fluorine is also 7. So this is 14 by 2, this is 7. 7 means it is sp3 d3 hybridization. So pentagonal bipyramidal if you take, so that is pentagon. First I am going to create a pentagon like this. This is a pentagon. This is a kind of pentagon. Fluorine, 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 fluorine and fluorine. Create a pentagon like this. And bipyramidal we are saying, so take one more fluorine here and cut the pyramid like this. This is the the pentagonal bipyramidal structure of iodine heptafluoride, and that is square planar bipyramidal, that is BrF5 molecule. Now if you go for the next part of the discussion, that is, I can say that preparation and properties of chlorine. If we take, that is, first we'll go with the preparation. In the preparation of chlorine, you can take manganese dioxide when treated with the HCl, it forms manganese chloride plus chlorine plus H2O. If you take, yes, we can balance the equation. I think if I am going to take 2 over here, then I think if I am going to take over here, yes, we can prepare the chlorine gas. We got a chlorine gas here. And also manganese dioxide when treated with NaCl in the presence of H2SO4 also we can prepare. Of course, you are going to get manganese chloride plus chlorine plus sodium bisulfate. So manganese dioxide when treated with the brine solution, this is brine solution, and this is acid, and this is metal oxide. You are getting manganese chloride, chlorine gas, and this is bisulfate, sodium bisulfate. So therefore what is happening here is like if you want to balance the equation, you are finding that there are 4 sulfates are there. Here we have 4 sulfates, so here also we have 4 sulfates, and here we have total 2 plus 2, 4 chlorines are there. Yes, 4 chlorines are there. Yes, 4 sodiums, balanced, everything is balanced. Fine, the already 3 methods are over. Now potassium permanganate when treated with HCl also we can get KCl plus that is, you can take manganese. Potassium permanganate when treated with HCl we get potassium chloride plus chlorine gas plus manganese chloride plus water. So suppose if I am taking here 16 moles of hydrochloric acid, then obviously I have to take 8 moles of water. Then number of hydrogens are balanced, but I think number of oxygens have not been balanced. So suppose if I am going to take 2 over here, number of oxygens are balanced, so therefore 2, take 2 over here. Then manganese also, if I am going to take 2 over here, I think the rest of the reaction is already balanced. So this is the best method of preparing, that is the chlorine gas. These 3 comes under the lab method. These are the lab methods. And we have the industrial method. If you go for the industrial method, that we call it as the Deacon's method. And in the Deacon's method, we take hydrochloric acid when treated with the oxygen, you get chlorine gas plus H2O liquid. So here that is cupric chloride acting as a catalyst. The catalyst is cupric chloride, and the temperature is around 723 Kelvin temperature, and this is how we prepare. This is how we try to prepare the chlorine gas using the Deacon's method. And apart from Deacon's method, that is the Nelson's method, Nelson's cell electrolytic method. For the aqueous brine solution. If you take, so actually NaCl aqueous when subjected to electrolysis, it gives anode plus cathode electrodes. At anode you have the chlorine gas, and at cathode you have NaOH, and that is H2 gas. So there is an interference. Between the chlorine gas and NaOH. So therefore there is an unwanted reaction taking place. So therefore NaOH, which is obtained at the cathode during the Nelson cell process, it can give you NaCl plus NaClO plus H2O. This is the interference reaction taking place in the Nelson cell methods. And these are all the different methods where we can prepare the chlorine, both through lab method as well as through the industrial method. And now we are going to study the chemical properties of chlorine.